Okay, so today's kind of the last official day that I have planned for this class. So next week, obviously, we still have lectures, but um, you know, unless someone requests a specific feature in the but today I want to go over buffering and stress testing. So there's a lecture portion with a short, city portion with a short, and so we're trying to knock both of them out in the same day. So this activity, this is not something that I'm going to do, because I know you guys are focused on project 15. So, this is just something that's just for you. This is something you can use on the final. It does make sense, especially if you're going to be using constructive mode. All right, but besides that, for next week is just all open. Next week, so helpful for you guys. All right, any questions I can answer before we? Okay, all right. So let's start with the lecture. All right. So the topic for today, and the topic for ANSYS is buffering and stress. Okay. Well, I chose this as the final topic in here. So it's kind of focused on, the kind of how we started. So, a lot of times when you're doing kind of an analysis and you're doing it in a structural, setting, a lot of times you're interested in seeing whether your part or whether assembly or structure, whether it's going to fail under the assignment. That's common way that we use FEA. Many applications of FEA, but it is very common to use it. And remember, the way that we typically do this is that from the FEA simulation, we're able to compute, the equivalent stress distribution. From that equivalent stress distribution, if that equivalent stress, oh, oh, oh,
Is that better for the audio? Okay. Yeah, for some reason the microphone was switched to a different one somewhere in the classroom. I was noticing that the microphone wasn't going up as much. So thank you. Thank you guys for pointing that out. Okay, anyway, so like I was saying, so FEA normally it can be used to determine if a part will fail. And the way that we do that is by computing the equivalent stress and comparing that equivalent stress to the yield strength of the material. Right. And so what we basically says that if the computed equivalent stress was greater than the yield strength, then your part was going to fail, right? So this type of failure is very specific, and so this is actually called material failure. Okay. It's named so because the failure is due to the material actually kind of breaking apart. It just can't sustain that stress. Okay. Now there are other ways for a product to fail or a structure to fail. We've already discussed a few of them, and so one way that we discussed just in the last activity was through resonance and vibrations. Okay. Okay. So there's resonance, there's dynamic loading. So, there's, material failure is not the only way, although material failure is probably the most common. Okay. But another way that we haven't covered yet in the class is buckling. Right. So buckling is a phenomenon that occurs specifically when you are applying a compressive load to your structure. So basically any kind of load that's going to squeeze your structure together has the possibility of inducing buckling in your system. Okay. Okay. So what is buckling and what makes buckling different from material failure? Okay. So the exact definition for buckling is the reduction of bending strength in a material due to the action of compressive stresses. Okay. Okay, so we haven't talked specifically about bending stiffness before, but bending stiffness refers to a structure's ability to resist large bending deformations. Okay. So basically what this is saying is that if you're going to be supplying a compressive load to your structure, it's going to make it a lot more sensitive to bending stresses and bending deformations. Okay. Okay. So let me give you an example, probably something that you've all seen or probably done at some point. Okay. So probably the most, I would say, visible example for buckling that occurs in your day-to-day life is in the crumpling of an aluminum can. Okay. So maybe you just drank a soda, or maybe you drank like a juice or something, or a can of coffee, and you have an empty can, right? And so typically what people do before they take their can and throw it in the recycle bin is that people like to smash the can down, right? And so, what that looks like is, maybe you have a can, and so this can is of some generic soda because I'm not sponsored by any soda company. Okay. And then what you can do is you can apply a compressive loading, right? So you can apply this loading, aluminum cans are fragile enough that you can smash it with your hand. So you can kind of smash it together, or you can put it on the ground and step on it with your foot. Okay. And then what happens is that, what we observe is that the entire structure kind of crumples in on itself. And so, once it's kind of fully compressed, it looks kind of something like this. And so the entire length of the can goes down. Okay. But most importantly, if you look at the sides of the can, right? they have this kind of like jaggedy, kind of wavy kind of structure to them. Okay. It basically almost looks like, the thin sheet of aluminum that the can's made of is kind of folding in over itself, or it's causing all these little folds and getting really kind of crinkled up. Okay, so that's an example of buckling. And so, when you apply that compressive loading to the can, right, a couple of things are actually happening when you apply the compressive load, okay? So on the surface, when you look at a situation like this, you may think that, oh, we applied enough compressive force such that we achieve material failure in the can, okay? And that can happen, that it is possible to apply enough force for that to happen. But likely what's happening first is that you're causing buckling of the aluminum structure before you get to material failure, okay? So that's the thing with buckling is that, buckling usually will occur well before material failure. And so it's always something to keep in mind when you have a structure that's being subjected to compressive loads, okay? Okay. Right, so when you apply your compressive load to the can, buckling will cause the bending stiffness to decrease. And then what's going to happen then is that, any kind of imperfection or any kind of, load that's applied in the transverse direction, right? It could just be just from, an uneven or rough surface of the can itself. That's going to cause the entire structure to just kind of crumple in on itself. Okay. Okay, hence you get this kind of phenomenon here. So if you want to try this at home, next time that you finish a can of soda or next time you finish a can of anything, right? Don't just smash the can over all in one step. Try to take the can and try to kind of smash it slowly, right? And then if you kind of apply just enough force, you should see this kind of buckling motion or buckling behavior happen in real time. Normally it happens way too fast for people to really observe. But if you kind of really take your time with it, it's really kind of an interesting kind of pattern that you can see. Okay. Any questions on this so far? Okay. All right. So what causes buckling? Well, buckling is actually the opposite of something known as the stress stiffening effect. Okay. And so the stress stiffening effect basically says that, as you apply tensile stress to an object, then its bending strength is actually going to go up. And so this is something that you can observe as well. So if you take like a string or even a wire, right? And so if you try to bend it, right? So if you take just a normal string, right? Like say this is just like a loose string, so maybe you take butcher's twine from your kitchen or something like that, okay? And so if you don't apply any tension and you try to pull up on it, so let's say that you take your finger and you just pull up on the middle of the string right here, right? The entire string is going to deform, right? And so you get something that maybe it looks like that, right? So without any tensile force, the string bends very easily because the bending strength is low, right? Now, if you take that same string and if you pull it taut, so let's say that you take each end of the string and you pull it apart, right? So that the entire string is taut like this, right? So let's say that you're applying a tensile force equal and opposite in both directions. Maybe you tie it to a wall or something like that, okay? If you try to do the same thing, where if you try to, pull on it in the middle, it's going to be a lot more difficult to bend because of that tensile strength, right? So stress stiffening, that's kind of what we call this effect, where when you apply tension to an object, it makes it a lot more difficult to bend versus whether you weren't applying that object that tensile force. If you want kind of a physical explanation of the stress stiffening effect, basically what happens is that when you apply a tensile stress or tensile force to an object, it becomes a lot more difficult for shearing stresses to occur, just because all the stresses are going to be kind of aligned with that tensile force. And so what happens when you bend an object is that shearing forces are pretty significant. And so when you apply that tensile force, then it makes it harder for that shearing to occur. Now, the opposite is true in compression. So when you compress an object together, because of conservation of mass, when you push an object together, the molecules get closer and closer, it becomes easier for shearing stresses and shearing motion to occur. Hence, that's kind of what causes the buckling. Okay. So normally when you are simulating something within ANSYS and you're using a simple linear material, buckling is not something that you are simulating because buckling is a non-linear effect. Okay. So there are kind of two ways for you to observe buckling within ANSYS. So number one, kind of the easy way, but also kind of the more time-consuming way, is to turn on large deformations. Okay. And so if you recall, from our discussion of nonlinear effects, maybe about 2 months ago, we talked about this large deformation toggle. So some of you have experimented with this already in the activities, but turning on large deformations turns on a lot of different nonlinear effects occurring. So by turning it on, you're able to observe buckling, and that's something that you're going to do in the activity as well. Okay, so that's the first way. Probably the most effortless way is just you just click a check mark. The second way is to use a separate tool known as eigenvalue buckling. Okay. And so eigenvalue buckling is a separate tool within ANSYS, so very similar to modal analysis. where you can very quickly determine, the effects of buckling in your structure. Okay, and so we'll see a bit of that in the activity as well. Okay. Any questions on this? Okay, all right, so let me just show you a very quick example here. Just so that you can kind of know what to expect when you're looking at buckling, at least when you have large deformations turned on. Okay. So let's look at a simple beam that's exposed to an axial force as well as a transverse force on top. Okay, so let's say we have a simply supported beam here. So we have a beam with a pin support on the left side. On the right side, we have a roller. Okay. So on this beam, I'm going to be supplying a axial force F, right? So the way I'm drawing it right now, the force F is going in the tensile direction, but we are going to reverse it eventually. And then on top, we're going to have a transverse load that's going to be distributed all evenly across the top of the beam. Okay, and we'll call this P of X. Okay. Okay. So for this example here, we're going to keep P constant. So P is going to be distributed load. We're going to keep that constant throughout all of our trials. Okay. So that's not something that we're going to change. But what we are going to change is we're going to change the value of F. And so we're going to change it from a fully tensile load to a fully compressive load. And what we're going to do is we're going to observe the deformations that take place from the simulation. Okay. So to make this easy, let's just graph the results. Okay. So I'm showing you this because you're going to produce a similar graph in the activity. Well, that's if you do the activity. Okay. All right. So for this graph, we're going to have on the vertical axis here, we're going to have total deformation or beam deflection. Okay. And then on the horizontal axis, we're going to have basically the value for F. Okay. All right, so I'm going to set a 0 point here. So I'm going to set a point here, 0. Okay. And so to the right of this dotted line, these are going to be tensile forces. Okay. So typically tensile forces are given as positive values. Okay. And then to the left of this line, we're going to show we're going to have compressive forces. Okay. Compressive forces or compressive stresses normally are given by a negative value. All right. And so what you're going to see, very interestingly, is that, if you look at the amount of beam deformation, it actually goes up the more compressive loads that we have. And so the graph, doesn't quite look like a straight line, but it is straight-ish. The graph is going to look something like this. Okay. So what's happening here is that as we apply, well, let's look at the right first. So as we apply higher and higher magnitudes of tensile force, the stress stiffening effect takes greater and greater effect. Okay. Whereas on the left-hand side, we're seeing larger and larger values of the deformation. So that tells us that as we apply more and more compressive loads, then buckling is taking place, more and more. Okay. And so these results here, you can simulate this. And remember, in order to get these results, you have to turn on large deformations. All right. So when you do this part, I guess if you do this part, if you do this activity, you're going to produce a plot that looks very similar to. Okay. All right. Any questions on this? Okay. All right. So the interesting thing here is that, eventually, if you continue to increase the magnitude of the compressive force, eventually you're just going to get complete buckling failure. And so what that looks like is the deformation is just going to get to some extreme value. So let's say that, at this point right here, we're going to have complete buckling failure. So buckling failure occurs when the bending strength of the material goes down to 0. Okay. And so when the bending strength is 0, it's not able to resist any bending deformation at all. And so what you have is kind of a very sharp increase of the deformation around that bending failure. Okay, buckling failure. And then eventually, your entire structure will just kind of fail catastrophically, just like a soda can when you stomp on it. Okay. Okay. All right, so that's one option to for observing the buckling phenomenon within ANSYS is just simply if you have compressive loads, turn on the large deformations and then see what occurs. Okay. But remember, the downsides of running large deformations is that it can be a bit expensive, especially when you have very, very large, number of elements in your mesh. Okay. And sometimes you're interested, maybe you have a structure that is stable, in its base state, but you want to find out, things like the factor of safety. So how much more can you increase the load before failure occurs? Okay. And so, of course, that's a problem that, I think everyone in this class is familiar with as well, right? And so a lot of the activity is going to have something like this. And the way that you found it was you just iteratively kind of kept running simulations, which, as everyone knows in this class is not the most exciting thing to do. And so, what if you don't want to keep sitting there at the computer and incrementally increasing the load until failure occurs? Because that takes a lot of time, especially when you are running with large deformations on. Maybe you can't afford to sit at your computer for 3 hours and just modifying numbers. There is an easier way to answer that question, which is to use the eigenvalue buckling tool within ANSYS. Okay. So eigenvalue buckling is a quick tool that you can use in ANSYS that essentially is going to tell you how much you can magnify your loads before buckling will occur. Okay. So the way eigenvalue buckling is going to show you results is that it's going to show you results in terms of a load multiplier. And so what that basically means that, if you apply that multiplier to all of the loads in your model, then ANSYS will predict that that buckling will occur. Okay. And so in that sense, it's a very straightforward analysis. And so you basically set up a static structural simulation, and then you link it together with eigenvalue buckling, and then you just let it go. And then it tells you right away, you can multiply your loads by 2, by 3, by 4, by 4.5, before buckling can occur. Okay. Okay. Now, the other thing that's interesting here is that not only can it show you the load multiplier, but it can show you how the buckling is going to occur as well. And so that's called the buckling modes. Okay. So just like we saw the resonant modes or the harmonic modes with modal analysis, right? You can see, if buckling were to occur at this specific load multiplier, it's going to show you exactly which part of your structure is going to fail in buckling. Okay. And then just like with modal analysis, when you're viewing these buckling modes, just be aware that this is just for visualization only. These aren't true buckling, deformations. And so, just kind of keep that in mind. Okay. All right. Any questions on this before we jump into the activity? Okay. All right. So for the activity, remember this activity 8 is not going to be collected. If anything, if you just want to kind of watch and observe, that's fine with me. Okay. All right. So I'm going to go ahead and switch to the computer screen here. Okay. All right. So if you go to the Canvas site, so I didn't create a formal assignment for this because it's not something that I'm collecting. But if you go under Files and you click on assignments here, okay, you'll see that I have ANSYS Activity 8. And so, of course, this is not going to be collected, so it doesn't have a due date. Well, as soon as this loads, you'll see that it doesn't have a due date, okay? But what we're going to do in this example is that we have this kind of very simple truss structure here, and we're going to be applying loads to the structure. First of all, we're going to be observing the stress stiffening effect, and then you're going to see how the eigenvalue buckling works. So very straightforward activity. If you do it, it's not going to take you long at all. It's mostly just to illustrate to you how the eigenvalue buckling works. Okay. Okay. So if you want to do the activity, if you want to follow along, there is an ANSYS file for this. And so if you go to the file folder, you'll see the very first ANSYS file here is called 3D_truss.agdb. Okay. You can go ahead and download that. And we're going to use that as our model for this activity. Okay. All right. So let's go ahead and open up Workbench. And we will go from there. All right. Okay, so we have Workbench opened up. Okay, so first thing we're going to do is we are going to do a static structural analysis, and so we're going to observe the stress stiffening effect, using the large deformations, the nonlinear deformations within ANSYS itself. Okay. All right, so let's take static structural and let's click and drag it to the project schematic here. Okay. All right, then once you've done that, let's go ahead and change or import the geometry. So go ahead and right click on geometry, import, browse. And so go ahead and load in that 3D truss.agdb. Okay. So I don't think we're going to change the material. Yeah, we're not going to change the material. So let's go ahead and let's go ahead and load in ANSYS mechanical. So let's go ahead and double click on model here. All right, so there is our geometry. And so it's a little bit hard to see. Probably if you're in the classroom, it's even harder. But there is a truss structure here. It's just that everything has been converted to beams. Okay. So I've converted everything here to beams just to kind of simplify the calculations. You don't have to do this in a beam structure, so you can do this with solid elements just fine. It's just that I chose beams just to make things a bit easier. Okay. Okay. And if you look at the geometry here, you can see it's actually all one structure as well. So each of these beams is, they're all together into one assembly. Okay, so first let's go ahead and generate our mesh. So let's go ahead and right click this and generate. I just want to see how many elements that we have here. Okay. So you can see with a simple beam structure here, we are very efficient in the meshing. So we're able to produce a mesh with 205 elements. That's a little bit too small, and so I do want to increase this a bit. So let's, it might be easier. Okay, so if we change the unit system to meters, let's go ahead and change the element size. Let's change it to 0.1 meters. Okay, let's see what that gets us. Okay, so that's a bit better. So that gets our element count up to 860. Let's go a bit further down. So let's go with 0.05 elements. I want to get something that's at least 1,000 for this. Okay, that's perfect. So we have an element count of about 1,700. I think that'll be plenty for our purposes here. Okay. Okay, so next thing we're going to do is we're going to apply the loads and constraints. And so first thing, let's go ahead and apply our fixed constraints. And so the setting for this truss structure is that it's sitting on the ground. So let's add our fixed supports first, because that's something I forgot to do last time. Okay. So we're going to add our fixed supports, and we're going to touch all of the different bottoms of the legs down here. So we're going to go on point selector mode, hit this point, hit that point. It's a bit tough because the model is so translucent. Okay, so that should be good. Okay, so we should have 4 vertices for our fixed supports. Okay, and then let's go ahead and add in our load. So first thing we're going to add is we need to add a load that's going to compress this entire structure. Okay, so now even though the structure is made completely of beams, it is quite complex in that we have beams going in all different directions here. And so we're going to add a compressive force on the top, and that's going to compress the entire structure overall. But the buckling effect in each of the different elements is going to be different here because of the geometry. Okay. Okay, so let's go ahead and add a force. Okay. So first thing I'm going to do is I'm going to add a force to the top, and so I'm going to add a force on the left side and the right side, and so that's going to go ahead and hit apply. Okay. All right, and so because we want this force to apply a compressive load, I'm going to apply that force in the negative z direction. So let's go ahead and switch this components to the z direction, and let's change the units to pounds, just because that's what I have my handout in. And so let's set this to minus 5,000 pounds. So that's going to apply a compressive force downwards into the structure, okay? And just so that we'll have some buckling that's going to occur, we're going to help that out by applying some transverse loads as well. And so our transverse loads are not going to be high magnitudes at all. Remember, the whole idea with buckling is that it reduces the bending strength. So even a very modest amount of bending force or bending load is enough to cause, bending failure. Okay. Okay. So let's add another force. Boundary condition here. Okay. So I'm going to apply a transverse load to this beam right here. Okay. And I'm going to apply that load in the X direction. So let's change this to components and change this to just 100 pounds in the X direction. So, a full order of magnitude less than what we had above. Okay. And I'm going to do the same thing on another component here. Let's do it on this leg right here. All right, let's actually grab this entire leg structure. Okay, and so once again, I'm going to apply this load in terms of its components and apply a load in the minus X direction, minus 100 pounds. Okay. Okay, so the purpose of load 2 and load 3 here, that's just to provide just a modest amount of bending, just so that we can more easily observe the buckling phenomenon. Okay, so actually let me label these. So let me call this axial force. I'm going to call force 2. This will be bending force 1. And this one here will be bending force 2. Okay. Okay. All right. Any questions on this so far? Okay, good. Okay, so before we start to run the simulation, let's go ahead and turn on large deflections. Okay. So first thing is we're going to go under analysis settings here and turn on this large deflections. Okay. Just so that we can observe the buckling phenomenon. Okay. Okay. All right. So for the results here, let's go ahead and observe the deformation. So let's go ahead and observe total deformation here. Okay. All right. And the other thing that we're going to do, something that's unique to this structure here, just because it's all beams. Usually when you have a beam structure like this or a truss structure, usually you want to display the compressive or tensile force in each of the different members. Okay, so you can actually do that. So if you have a structure that's completely comprised of beams, what you can do is you can right-click on solution A6, go down to beam results, okay, or excuse me, beam tool, and then let's add the beam tool here. Okay. And so this will allow us to view the stresses within each of the beam elements, and it'll tell us whether we have a compressive or tensile load. Okay. All right, so let's go ahead and run the simulation. Okay, so simulation was pretty quick just because we have just a very simple stress here. Okay. And what you should see here is that all of the deformation is concentrated into the two beams that we've applied the transverse load on. Okay. And so in fact here, you can see that the maximum deformation here is 0.022 feet. Actually, let's display these in inches. That might be a little bit easier to see. Okay, so we have deformations here of about 0.27 inches. So let's write that down. Okay, good. Okay, so we observed this deformation when we had, a compressive force of 5,000 pounds. Okay, let's change this. So let's see how our deformation is going to change. But instead of a compressive force, let's change this to a tensile force. So I'm going to change this load magnitude to positive 5,000. Okay, and let's go ahead and rerun our simulation, and let's observe the deformation that occurs from this change right here. Okay. So all I did was I just changed the direction of the force here. So instead of a compressive force, it's now tensile, but our two transverse forces are the same. Okay. Okay, and so you can see just by changing the direction of the force, our deformation here is a lot less. And so, now we get a deformation of 0.022 to 2 inches. Okay. So that right there is the stress stiffening effect in action. So, when you apply a compressive force, that causes the bending strength to decrease, and so that increases your deformation. When you apply a tensile force, your bending strength is increasing, and thus decreases your bending deformation. Okay. Okay, so if you look at the activity, let me bring it back up. Okay. So if you're following along and you're kind of interested in seeing this, what you can do is then you can run the same simulation, but I want you to vary the axial load from 10,000 pounds, so that's full tension, to minus 10,000 pounds, which is full compression, in increments of 1,000. And then what you can do then is you can observe how the deformation changes within the truss itself. Okay. And what you should see is that as you modify the loading, right? And this is just the axial load, you're going to see that the bending deformation is going to change actually fairly rapidly or fairly significantly within that range. Okay. Okay. So that's something that you can do if you're interested in it. Of course, I'm not collecting this, and also I don't want to run 20 simulations right now, and so that's something that you can do on your own if you're interested. Okay. Okay. Any questions on this so far? Okay, good. Okay, and so if you wanted to use buckling for your final project, this is something that you can do. And so you can observe the stress stiffening effect by modifying the amount of compressive or tensile load and seeing how the bending deformations change as you change the magnitude of that, the magnitude and the sign of that. Okay. Okay. So the second thing we're going to do in this activity is we're going to observe eigenvalue buckling. Okay. Okay. So to observe eigenvalue buckling, we're going to close out of mechanical here. Okay. And we're going to load in a separate tool. So, and so if you go to ANSYS, back to ANSYS workbench, you'll see that there is a tool here called eigenvalue buckling. Okay. So what I'm going to do is I'm going to drag and drop this where we're going to upload the solution into our eigenvalue buckling. So you're going to click and drag eigenvalue buckling right on top of solution for your static structural simulation. Okay. All right, and then once you do that, you're going to double click on setup, and that's going to open up ANSYS Mechanical one more time. Okay, all right, so we're back in mechanical. Okay. Oh, one thing that we need to do in order to make eigenvalue buckling work is we need to make sure that we have a compressive load. So I'm gonna go ahead and change this. So I'm gonna change this to minus 1,000, just so that we're in the compressive form. Okay. And let me do this. Let me go ahead and solve our static structural again, just so that we're starting from a point where we have a compressive load. Okay. But eigenvalue buckling will not work unless you have a compressive load in your structure. Okay. Okay. All right. So first thing we're going to do is we're going to change a few of the settings. Okay. All right. So first thing we're going to do is we're going to change this setting for maximum modes defined. And so this is under eigenvalue buckling. And so we're going to change this to 6. Okay. So this is going to let us view the first 6, buckling modes. Okay. Okay. And then under solver controls here, one thing that we're going to do is we're going to change this setting here. Okay. So one thing that eigenvalue buckling can do is that, if you have a complex loading scenario, you may get buckling if the loads were reversed. Okay. And so, this setting here for include negative load multiplier will allow you to view those situations. But since we have a very simple situation here, there's really no need for us to view the negative multipliers. And so I'm just going to hit no. Okay. All right. And so with that in mind, and so with those two changes, let's go ahead and hit solve. Okay. and you're gonna see it's a very, very fast solution, right? And then when you click on solution B6, in the bottom right-hand corner of the screen, you're gonna see all the load multipliers, okay? So this is telling us that, if we want to see buckling for this structure, then we would need to multiply our load by 11.33 in order to observe buckling, okay? All right. And so that's basically what eigenvalue buckling is. And so you basically obtain these load multipliers, and you can see, how endangered your structure is from buckling. So, one way that you can interpret these load multipliers is that you can interpret them as if they were a factor of safety. And so that means you can include, if you increase your loads by, that means the structure can withstand loading that's over 10 times the base case, and it will still be fine. So that's good. Okay. All right, one of the things that I'll show you is you can view the buckling loads for this. And so just like we did for the modal analysis, you can highlight all of the load multipliers here, right click and then click on create mode shape results. Okay. And so that's going to create different deformation plots. And so if we click solve, right? And if you click on each of these different plots here, you can see where the buckling is going to take place and more importantly, how it's going to take place, okay? Okay, so the first buckling mode right here, you can see is going to occur in this part of the structure here, okay? Second buckling mode, you can see the failure is actually going to be in this part of the structure right here, okay? So this is actually really interesting. And so, this will tell you which parts of your structure are going to fail first in buckling, and then the second failure point and third failure point and so on and so forth, okay? So again, this can tell, maybe this can give you hints in terms of how to strengthen your structure, from buckling, right? Okay, so you can see the fourth mode right here is really interesting. Most of the failure occurs up top here, but you do see a little bit of buckling in the other parts down there. Okay. All right, 5 is also kind of a hybrid mode, and 6 also as well. Okay. All right. Any questions on buckling? Yes.
Would you keep the line deflection on?
Yes, keep it on. Exactly. Yeah. Yeah. So eigenvalue buckling it's not actually going to use the large deflections, but just keep it on just to make sure it's simulated. All right. Any other questions on buckling? Okay. All right. So that's all I had planned for today. So actually, we got the lecture and the activity done in the same day, which is good. So that means all of next week is completely free. And so if there's a particular topic, and so I know everyone's kind of at this point kind of finalizing their final project topics. And so if there's a particular topic you want me to go through, if you can look at the handouts that I have posted on Canvas. If there's anything particular you want me to go over together, you can let me know, and so I can cover that next week. Or if you guys would rather just have open office hours, and so you guys can just come in, just flag me down, and we can have we can just talk about your project and we can work through the issues. That's fine too. Just let me know. But that's pretty much all the content I have for 540. So from here on out, it's just supporting your guys' project. So so I'll stick around for today. So there's about 20 more minutes, so I'll stick around till 6:45. But if you guys are heading out, thank you guys for coming. Hope you guys have a good weekend, and I will see you guys next week. Yeah.
So for like the difference in mode, how we create blocks.
Yeah.
What is that thing to find out?
Yeah, so this is just showing for buckling, this is just telling you where it's but I don't like the way ANSYS does this, where it actually says, this is the deformation, but this is not true deformation. So,
I don't know.
exactly, so this just tells you the shape and where.
Well, these are like basically different occurrences.
Exactly.
I think this could be the first time that I put bubbling.
Exactly. Exactly.
The same thing goes for vibration.
Exactly, so for vibration, you'll see the resonant modes here, so this will be the first frequency of the resonant occurs,
Yeah.
second time, third time, fourth time.
That means like increasing the amount of frequencies that you get.
Exactly.
Okay, okay, thank you. These are different simulations based on the number they give you.
Exactly, yeah,
Okay.
yeah, so, exactly, yeah, yeah, so basically to produce those, for this one in particular, they multiplied all the modes by 11, and then they basically just highlighted to you which parts of the structure will fail first.
If we put that up.
Exactly, exactly.
And let's say I want to use one of those nodes just to test it out,
Mhm.
would that be now a true?
Exactly, yeah. So if you took this, and so let's say that you actually want to test it out, you would then go back to your modes here and then multiply this mode here by 11.3. And then same thing for these ones too. So kind of the thing with eigenvalue buckling is that, it applies this mode multiplier to every single one of your modes. So it's not just a compressive one. It actually, because ANSYS can't really differentiate in terms of which ones are compressive, which ones are not.
Yeah.
And so, you'd have to multiply all three of your modes by 11.33 in order to get buckling in this case. Yeah.
That-
Yeah.
Thank you.
Mhm. Right. Yeah, so for vibration, you have to do it a little bit differently. So you have to use harmonic response. So that was kind of the second part of the molecular activity. So exactly. Yeah. Mhm.
actual vibration analysis on the story now, because I was thinking of doing it well,
Yeah,
but it has too many components.
oh, yeah, I can see that.
Yeah.
Yeah, it definitely is. So for a four-way valve, um, I mean, it's definitely possible to do a vibrational analysis on it. It's just more justifying it. So for a valve like that, I would say, maybe it's like a component of an engine. And so there's vibrational load happening kind of around it. That might be a case where, you can do that. It's not a geometry that I would normally associate with like resonance failure. But it is still possible to get resonance occurring. Um, Oh, one case could be, maybe there's like vibrations coming from inside the fluid. So maybe there's like pressure waves that are occurring in the fluid. Yeah, I think that's, and it might rupture from the inside. Yeah, I think that's definitely valid. Oh, yeah. Yeah. A lot of options.